Looks like it. Okay, yeah, we're recording. Good. Right, so to get started, let's see. First we'll put in some of our data. So I'm just going to make up some numbers. So what is on your x-axis? For the electricity one, what will be on the x-axis? Dude, just answer my question. What is on the x-axis in the electricity experiment? V. V is on the x-axis, and what's on the y-axis? I. Okay, so I'll just use x and y, but for you it will be v and I, or for Newton's law, which would it be? For Newton's one, which will be on the graph?
Speed and v and acceleration.
No, no.
Wait, I have to get.
No, I'll let you figure it out.
I over against a.
What against what?
Something against acceleration.
Correct, something, yes, and acceleration, yes.
Expression of the y.
It doesn't matter, I've told you already, I'll let you find it yourself.
So V
Huh?
V and U.
Oh, v and acceleration.
No, stop guessing.
VU and acceleration.
No.
I have written down in my other book too.
No. Right, so, I'll just write x and y. So I'll put in some numbers. So let's just say x is like 1, 2.1, 2.9, 3.1, 3.9, 4. And then let's say y is 1.1, 2, 3,
Okay, force against acceleration.
yes, congratulations on reason.
4.
4.1. No, look up. No, look up. I'm only going to do this once. So you can type along with me. Why are you moving?
You can't see from this.
Get your laptop so you can do it as well. Get your laptop so you can do it as well. Right. So first we'll, after we have inputted our data, you can input the same data if you want. We'll make our graph. So I'm not using Excel, but it'll be very similar. I'll highlight my data and then we'll do insert chart. And again, it's going to be the same in Excel, insert graph or insert chart. And just like in Excel, you want to scatter. Next.
For both of them.
For both of what?
Graphs.
Yes, everything here is the same for both. Right. So onto the part where you have to input information. So delete this legend and make sure you have an X and a Y axis. The title should be something like Y against X. But of course you need to make sure, and then whatever, experiment 3. X-axis, please don't forget to have the units. So for example, maybe my one is acceleration and force, or maybe it's current and voltage. It doesn't matter. So what you have on the x-axis is x-axis slash and then the units for x. And then on the y-axis is y, whatever the y is, slash, and the units for y, whatever they are.
For example, force and unit or
Newton and meters per second squared, whatever. Okay. Right, yes? So this is your graph. So everything, what?
No.
What's wrong? Look up. Everything here is what you need. Okay. What you're missing now is the straight line. So Excel can put in the line for you. In Excel, it's not called best fit line, it's called trend line. Yeah, now you make sure you have this thing highlighted, and this thing as well would be nice. The equation and what's called this coefficient. I'll explain them now in a moment. And let me just move them a little bit over to here. Right. So what you have here, the first is the equation of the line. So you can actually see exactly what the slope is. What's the slope here? Can you look at this equation and tell me what the slope is? Tell me what the slope is, please. 1.01, isn't it? Why is it 1.0185?
The slope?
Yes, because it's the number in front of the x.
Okay, I can't see what I'm figuring.
Yep.
After that it's minus?
Yes.
F of x, the value, and the minus 0 point something.
What?
That's
F
minus.
of x equals 1.018 x minus 0.0025.
After x it's minus?
Yeah, Fahad, what's wrong? It's
Not
not that small. What's wrong?
Just confirm it's
Yes.
minus?
Minus 0.0025
Then,
after the x. Is that what you're asking me?
yeah.
Yeah. Can you all see that? 1.01 blah 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 x minus 0.0025.
Okay.
Yeah, so what's the slope?
0.995.
No. What's the slope?
The triangle thing.
Oh, this is depressing. The slope is the number in front of the x, isn't it? From semester 1, week 1 maths. Y equals mx plus c.
Yeah.
Wake up! So what is the slope of this line? I've given you the equation of the line.
1.855.
Yes, this is the slope. And what is the intercept?
Intercept is 4.4.
Minus 0.0025.
Here it's not showing intercept.
Ah.
Yeah, it's math.
Yeah, it's basic math.
No, I didn't get what you were asking about, like from minus. Now I get to why the equation.
Yes?
So now I don't need to calculate. It's already calculated.
It's different.
Yes. The slope has been calculated by the program.
Yeah.
Yes.
I don't need to calculate it
By hand.
by hand.
Yes. The program is calculated. Now look, there is another thing here called the R squared. Do you see that?
Yeah, what's that?
Now, I haven't told you what this is, but this R squared tells you how well the points fit the line. So for example, let me change one of these points here. Let's change this to 0. Now notice that this point, or what was it previously actually? Let me change it to 1.9. So you see this first point has moved up. It's not quite as near the line.
Okay.
So does the line fit the data better or worse now? Worse. And you see the R squared has reduced.
Yeah.
So for example, if I reduce this to say 1, now you see it's become much worse, hasn't it?
Yeah.
And the R squared has reduced again. So in other words, the R squared is a way to measure how well the line fits the points. If the R squared is equal to 1, it means a perfect fit. If the R squared equals 0, it means no fit whatsoever. Your R squared should be 0.9 or greater. Okay? Yeah?
What's Oscar like?
What it is not something the engineering students need to know.
What's that?
How straight is the line?
Huh?
How straight is the line?
How straight are the points?
At the point.
Yes. Yeah. That's it. How to calculate it is not part of the course, either in physics or maths. So you just need to use it from Excel.
Okay, and also for the slope, I don't need to calculate afterwards.
Correct. Now, if you look here, I'm going to delete this graph now that the graph is finished, okay? Yes, I'm going to delete this graph now that the graph is finished. Any questions before I delete the graph?
Everything is clear.
I'm deleting the graph in 5 seconds unless there is a question. Fine, okay. Now, if you want to calculate the slope without using the graph, you can use this function in Excel called slope. So if you click the function button, and if you pick down here slope, you see it here? And pick next, then what you do, you highlight, see the way here, it says data y, highlight the y's. You see here data x, highlight the x. And what should the slope be? 1 point something, wasn't it? And there it is there. And likewise we can calculate the intercept. There's intercept. So the y's, let's calculate it. And then the x's. And what was the intercept? It was some negative number, wasn't it? And there it is there. Okay, so I'll just write here M and C. So I would like you to do this in Excel as well, to double check that, well, you need to for the next part anyways. But it matches, see? Yes? Is this okay so far? Yeah. Okay. Now, here, I'm going to write x again, and I'm going to write something called predicted y. Guys, you're looking at your laptop a bit too much. What are you checking on your laptop?
Changing a different so it's not the same.
What's not the same?
The graph thing and the
What's wrong with your graph?
so I'm just figuring out how to, like.
Because your numbers are different to mine, so that's why yours is different.
Okay, that's not the issue.
What's wrong?
I'm just trying to find out how to customize
But these are small details you can look up later. You should be focusing on the new thing. You can go to Google and type in how do I blank on my Excel graph. But what I'm showing you here right now is not something you can easily find on Google. Yes, so please, just think, please. Right, so what I'm going to show you next is, you know that y equals mx plus c. So what I'll just do is I'll copy these x values here. And what I'm writing here now is something called a predicted y. So this is the y you should get from your formula if you use x. So what's the formula? Mx plus c. So I click m times x plus, and then I click the c. But we need to put these dollar signs around the m and around the c like this. And this is Excel's way of saying that these are constants in the formula. So don't change them. Okay? Yeah, well I'll do it again, right? So what's the formula for y? Mx plus c. So equals m, here's m here, times x, here's x here, plus c.
Okay.
Now I'm putting dollar signs around the m and the c to tell Excel that this is a constant value.
Can I ask something?
Yes,
You put dollar sign between A and 9.
correct, around the letter.
And you put in, okay, then C2 is not, constant.
Correct, it's the x. Enter.
Yeah.
Now you see how this value, the predicted y, is slightly different to this value. And if I have a picture here, well I've deleted my graph, but if I can get a nice image here to show you. The reason for the difference is the points aren't perfectly on the line. So for example here, this one here, the point is at 1, but the line is slightly above 1. And here, the point is at 2, and the line is slightly below 2. So the predicted value is the value it should be on the line, and the actual value is the value you got from the experiment, and they should be slightly different. And if they're very different, it means the point is very far away from the line. Yeah?
This asking.
Yeah.
This line is not the best fit line into the street.
This is the best fit line here. It's the line that's going through all the points. The points are red here. Point, 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 point.
It's not through the points.
Huh?
It's not through the points.
Exactly, because none of the points line up, but it goes through the points as best it can. So like if there's 2 points here, it can't go through either of them, it'll just go in between them.
Yeah.
Yes.
It
So
will
what are
go-
you asking me?
The thing I have learned in like
Yeah.
the best fit line
Yeah.
is to when we draw in the graph
Yes.
that draw lines that nearest to be like more like most of them.
Yeah. But here you can't draw the line that goes through most of them because they're not lined up. The points are zigzagging. It goes up, down, up, down. So what's the question? Is there a question?
Stephen, you want y only for one point, is it?
For what?
Have to get y only for one time.
What do you mean? No. I did it once. And now I'm going to copy it down for all the points.
Okay. But
Yeah.
this one question, this one.
Yes.
So the x here is the same x here.
Yeah, the x is the same. So what we're doing here is, if the x is 1, what should the y be? It should be this. What was it though? It was 1.1. Okay? Now we'll do something similar for the y. This is the y, and this is the predicted x. Now, what we're doing here is we're going backwards. You have the y value, and you go across to the line and straight down. What is the x value you should get? So one way we can do this, I have my paint program closed, but you can just rearrange your formula to make the x the subject. Well, do I even need to write that down? Well, I better. So what we're doing is we're going to go backwards. If I know the y, go across to the line and down, what should the x be? This is called the predicted x.
Y minus c over n.
Yeah. So I didn't even need to open it, but I will anyways. So if y equals mx plus c, then x should be y minus c over m. So that's what I'll use in this formula here. So the y I'll copy. And then the formula for x, as you said, what does it equal?
Y minus.
Bracket y minus c, wasn't it?
Yeah. Over.
All over m. And what I'll do is I'll put the dollar signs over the constants, which is here is the c, and then here is the m. So I should have gotten 1.08 for x from the y, but what was it? 1.1. So it's pretty close. And again, I copy this down. Just like before.
Is that recorded?
This is being recorded. There's already a video on Moodle from last year on this as well. The video from last year might be a bit better to watch because I would sound less angry in that video. True story. Right. So now that we have the predicted y and the predicted x, we would like to know how different they are compared to the line. So we calculate something called the residual of y. Now, residual sounds like a fancy word. All the residual is the difference between what was predicted for the y and what you actually got.
Just minus.
Basically, yeah. Now we have to use a function called ABS. ABS means just give the positive number, absolutely positive. Don't care about the minus sign. So we do ABS, the y we actually got minus the predicted y. So you can see it's a small number. All of these will be small numbers. What do you think I do next? The residual of the x. So this is how different ABS the x was compared to, oh sorry, I should, well, it doesn't really matter. Sorry, how different the, hang on, some of the letters gone wrong here. X, yeah, sorry, I should go back to this one. No, x minus the predicted x. So again, that's also very small. Okay. So what these numbers, oh, and one thing to do then, I'll average these. So I'll just get average the residuals here. And then average this one as well. So these two numbers here are very important. Let me bold them. So what these numbers represent is, on average, how far away you are from the theoretical perfect line. So here, what is the y error here? Roughly, about 0.1 would you say, yeah? See this length here in red? That's about 0.1, isn't it? Like here is 1 unit, so this distance is about 0.1. What about this one here? 0.2, actually it would be nearly 1 unit, wouldn't it? 1 unit. What about here? 1.5, and here? Near 1. So if you average these errors, if you average these residuals, then you get on average how far wrong you were with the y. You can do the same with the x. So if you look here, if you bring the line to the x, that horizontal distance is like the x error. And here, that one is like the x error. Here, this is like the x error. Here, this is like the x error, and this one will be, again, a huge x error. It'll go all the way out to here, this distance here, because you need to draw the line up. So you can have this average x error and average y error. You want them to be small. In fact, in a perfect world, what should these numbers be? What should they be if everything was perfect?
0.
They should be 0. That the points should all fit on the line with no average x or y errors. They should just sit on the line. Yes? Okay. Right, so what we do is we calculate here the ratio of the two. So the residual y divided by the residual x, we get this number. And then what we also need to do is divide it by how many we have. So how many data points do we have? 1, 2, 3, 4, 5, 6. So I'll divide this ratio by 6. Yes. So this number here, this is your uncertainty of the slope. So for example, let's say the slope represents resistance, for example. What this number represents is how much error there is in estimating your resistance. So what value of slope did you get? Here you got 1.01. Is the resistance actually 1.01? Well, it could be, but there's a plus minus error here called the uncertainty. The uncertainty is 0.16. So for this one, you could actually say that the resistance could be as small as this minus this, or as big as this plus this. So the resistance, if you are using the slope to estimate it, you know that there's some error in the point, so the slope might be slightly off. This number here is a way of putting kind of boundaries on how much of a mistake you made in the experiment calculation. So here I can confidently say that we expect the resistance to be actually between 0.84 and 1.18.
we
You
have,
see, just a second, let me think here.
We have to put all this in the reports.
Let me think. Yeah. Sometimes you can put a 2 in this. Sometimes people are conservative. And by conservative I mean they want to play it extra safe. So what they do is they multiply their uncertainty by 2 to make it twice as big, just to be extra cautious. So if you do that, then you can of course will have a bigger range for your estimate. But at this level of physics, I don't think we're not trying to predict something really important where somebody's life will depend on it. So we can just use the regular value I showed you. You don't need to multiply it by 2 to be extra conservative. Now you need to do this for both the electricity one and for the Newton one. Now, question there was that? Yes. Yes.
Do we
Well,
have
you
to
hit
write
first. Yeah.
put all this in the report?
Yes. In your report, you need to explain this analysis you're doing. Okay. So, for example, you should try to explain what the residuals represent. They basically represent the difference between the point observed and the line of best fit drawn.
And do this for the two graphs, for the two.
Yes, the two,
Third one, fourth one.
third one and fourth one. Yes, Fahad.
do, we have to explain this in the word, step by step.
Oh yes,
And
yes,
analysis.
yes. So you would have. You see, this is something in research called reproducible research. In other words, a person reading your report, if they use the same computer program and the same instructions, they should get the same result. So in your analysis, you need to say not only the functions you used, for example, here you use the slope function and the intercept function, you should also state what version of Excel you used. Because you need to show to whoever's reading the report that if they do the same analysis steps, they will get the same value here. You might think all programs will give you the same results, and the answer is no. When we do statistics later in the semester, I will demonstrate to you an example whereby if you use OpenOffice, you get one answer, and if you use Excel, you get a different answer.
Why?
And you'll see that when we do the statistics.
Excel is more accurate.
No, it has nothing to do with accuracy. It has nothing to do with errors or mistakes. It just has a difference to do with how something is calculated.
Different function.
Same function, different answer. Because OpenOffice and Excel uses a different program to calculate it.
Open office means like Word.
No, I mean like what I'm using here is OpenOffice, LibreOffice.
Oh, okay, okay.
Yeah, but my point is, you might think that the same data and the same function will give you the same answer, but I'm telling you that different programs will give you a different answer for the same data and the same function in some situations. So this is why it's important in your analysis section not only to state what you did in Excel, but also what version of Excel you used.
If like we have like Excel, but we like you have the open office. If we
Oh, fine.
no,
Yeah.
okay.
Yeah, that's fine.
If it's a function or something different, then.
Oh yes, yeah. Now the function syntax is very similar. So for example, maybe the only difference between Office and Excel and whatever is that sometimes some programs use a comma and some use a semicolon. You see here? That is only possibly the only difference. Some might use a comma, some might use a semicolon.
But if we just follow the same.
But if you follow the same steps, open the function button, type in slope, and so on, that's fine.
That's cool.
Yeah. Okay.
So what's it in all of this?
So this is the uncertainty for the slope.
For the slope.
Yes.
Mm.
Now, I don't have time now, but at the start of the next lesson, for the handwritten reports, I'll show you how to calculate the uncertainty without using Excel. Now, of course, a handwritten calculation for uncertainty is not as accurate as this, but it's still very accurate. I mean, it's better than nothing. And I'll show you how to do that for Snell, the labs 1, 2, and 3, the handwritten report.
Yeah.
And you can also compare how accurate your handwritten estimate of the uncertainty was with basically the true value of the uncertainty from Excel.
Yeah, so the third one, fourth one, I need only the uncertainty for the slope.
Yes.
Oh,
Well, I mean, you have the uncertainty for the measurement in the table,
Yeah, I have them.
and then the slope, the uncertainty. So in the Newton's one, the slope represents the mass of the system. So, well, 1 over the mass. So your uncertainty is like, say, the mass of the system was between 1100 and 1200 grams. And if your actual mass was between these two numbers, then you've verified Newton's second law, or at least you've provided evidence for it. Turns out Newton was right after all. Yeah. Right. If you watched the video online for this lesson last year, you might notice in some calculations I put in a 2. So the video's a bit longer. Now the reason for that is I was trying to be more accurate last year. But I have a feeling that even like this, it's still more accurate than what they expect. But the problem is, the syllabus doesn't actually say how you would like the student to calculate the uncertainty. In fact, syllabus I don't even think has any uncertainty formulas in it. So it's kind of left up to me to decide what's most appropriate. So I feel like this will do just fine. I don't feel the need to put in a 2 to make it bigger and to be more conservative. Okay? But if you like, in your analysis section, you can say sometimes people use twice this value to be more conservative. But I don't even expect you to do that. If you did exactly this, that is good enough for me. Okay? Now please, for the love of everything in physics, alright, you need to have stuff being produced now. Okay, when is this due date?
Next Monday.
For the first draft?
So
No,
final
for the
draft.
final. For the final.
He said for the first one.
Do we have physics tomorrow?
Yeah,
Yeah.
one
Give
class.
us some more days, Stephen.
I can't give you more days. The dates were fixed. It's your fault for not doing this.
Yeah.
And hey, you're not the only one now. I don't see anybody else showing me a handwritten report. It's due on Monday.
Yeah.
Okay? So what you could do, you should get the handwritten report. Wait.
I'm sorry.
Get the handwritten report finished tonight.
Okay.
Okay? Show me it tomorrow. Then use Tuesday, Wednesday, Thursday, and Friday to type up Lab 3. Then on Friday you can show me what Lab 3 is like. I can check if there's any problems. And then I can say, good. You can now type Lab 4 the same way you type Lab 3 with the planning section at the front.
The planning section before the
Introduction.
Yeah, you can do it before or after. I don't really care.
But you said.
I would be so happy if I just get it.
It should be after introduction, I think.
I'll leave that for your call to make, okay? Maybe after would make more sense.
Yeah.
If you, I mean, some people, maybe you want to stick the planning section as an appendix at the back as well. That's fine too.
yeah, I think that is cool.
You want to do it as an appendix at the back. Okay, well, make sure you reference it in the introduction there, or the procedure part or whatever.
Just do it after introduction.
After you do the procedure, you could say something like, see appendix for the plan of this procedure or whatever, okay? In other words, acknowledge that it exists.
We can do like introduction, planning, and procedure.
Just follow this the way I had it on the slides. I don't even remember right now.
It was planning, introduction.
So your question is, should you do it the way that I showed you? Yes.
No. You showed us like planning,
Yes?
introduction.
Yes.
I'm saying, let's put the introduction, planning.
That's fine. Or even if you want to put the planning all the way at the back in an appendix as well. Either put the introduction either put the plan right before the introduction or right after the introduction, or stick the plan in an appendix at the back.
In the marking scheme, there's nothing like this, right? Or order.
The marking scheme says that the report should be well structured. So whatever choice you choose, just for goodness sake, make sure it's clear.
Okay.
Yeah. So if you feel it's more appropriate for your report to swap the two around, then it's totally fine. As long as it's still clear and logical, we are good.
Yeah,
Well,
I
I don't know what's good anymore.
this time